Last stage, we found the lowest precision that survives, FP8, then INT4 AWQ smooth quant, shrinking the model so it fits and runs faster. But a small fast model is not the same as a fast service. Now we serve it to real users at scale, and to do that you have to understand a strange fact. An LLM answers in two completely different motions, and one of them wastes almost all of your expensive GPU. On-screen hook serving is a memory problem wearing a compute costume. Spoken callback, we just quantize the weights down to FP8 and INT4. Now we ask how those weights actually get served. And why decode is the part that hurts. Every response happens in two phases. Phase 1 is reading the question. The model gets the whole prompt at once and processes every word in parallel. One big, fast matmul. This is prefill, and it is the reason you wait a moment before the first word appears. Phase 2 is writing the answer one word at a time. The model cannot write word 10 until it has written word 9, so this part is strictly sequential, and here is the catch. To produce just one new word, the model has to drag every single one of its weights out of memory. For a 70 billion model, that is over 100 gigabytes streamed from memory to compute one token. So look at what the GPU is doing during decode. The math is tiny, a single row of numbers times the weight matrices, but the memory pipe is maxed out reading those weights. The expensive part of the chip, the tensor cores, sits nearly idle, waiting on memory. That is what memory bandwidth bound means, and it is why the memory bandwidth number on a GPU spec sheet predicts decode speed better than the flops number, which leads to the magic trick of serving. If one weight read produces one token, that is a terrible value. But if you batch many users together, that same one expensive weight read produces a token for every single one of them. Batching turns wasted bandwidth into throughput almost for free. That one idea drives every optimization in this stage. Let me put the two phases on one diagram, then show you the four numbers that grade them. On the left, the prompt enters as one white block. On the right, the answer dribbles out one token at a time. Watch which resource lights up in each. Prefill first. The whole prompt, say 1000 tokens, enters as one block and runs through the model in a single parallel pass. The compute meter pins to the top. Tensor cores hot, the GPU saturated. This pass writes the keys and values for all 1000 tokens into the KV cache in one go. The clock that this drives is time to first token, TTFT. Now decode one token loops. Each step, an arrow reaches all the way back and reads the entire KV cache plus every weight just to produce the next single token, append its key and value, and repeat. The memory meter pins to the top while the compute meter drops near the floor. Memory bound. The clock this drives is inter-token latency, ITL, the typing speed. So the two phases drive two different numbers. Prefill drives TTFT, how long until you see anything. Decode drives ITL, how fast it types after that. End-to-end latency is the whole weight, and you always report the tails, P50, P95, P99, because the average hides the user who waited 4 seconds. And against all of that sits throughput, total tokens per second across everyone, and the one number finance cares about, tokens per second per GPU, which is cost. Here is the tension. As I grow the batch, throughput climbs and the GPU fills up, but each user's tokens now wait behind everyone else's, so latency climbs too. You cannot max both. So serving is choosing a point on this curve. Push batch size up until throughput is great, but you're about to break your latency promise. That bend is the SLA knee, and that is where you run. Interactive chat lives on the low latency end. An overnight batch job lives on the high throughput end. Now the obvious question, decode wastes the GPU and only batching saves it. So why can't we just batch everyone? because the old way of batching and the old way of storing the KV cache waste enormous memory. Next, the two inventions that fix exactly that: paged attention and continuous batching. Thanks for watching. Like and subscribe for more videos like this, and I'll see you in the next one.